Hello. So in this video, I want to justify the rule we have for repeated roots of the characteristic equation for a LHODECC, a linear homogeneous ODE with constant coefficients. Okay. So I'm going to do this by example. Suppose I have d minus 2 all cubed y equals 0. And that might sort of scare you, but believe me, that's a lot nicer than this original differential equation, okay? So this has the characteristic equation. If I plug in y is e to the rt, I get r minus 2 cubed equals 0. If I plug that in over here, I get r cubed minus 6r squared plus 12r minus a equals 0. In fact, this factors, I wouldn't really know that, but it factors as r minus 2 cubed equals 0. Wow, who would have thought? But anyway, some of you might remember that. Okay, but let's just deal with this, all right? So I have the roots are r is 2, 2, and 2. So what does the rule say? The general solution is y is c1 e to the 2t, all right, because the root of 2 gives you e to the 2t. And I can say c2 e to the 2t because I need to put a t in there, plus c3t squared e to the 2t, which I've mentioned is maybe the nicest way to think about it is this quadratic polynomial c1 plus c2t plus c3t squared times e to the 2t. All right. So let's try to figure out how we got that. So plugging in y is e to the rt says that r has got to be 2. So in fact, let's go back, and I'm not going to plug in y is e to the 2t exactly, but I know that's a solution. So let's instead make it u of t. I'm going to think, let's look for solutions that are of the form a function of t, a new function of t, we're calling it u of t, times e to the 2t. So I know that if u is any constant, I get a solution, but maybe I can get more. And indeed, I can get the rest of them. You see, this is the u of t we're going to be looking for. All right. So let's do a little calculation. What if I take d acting on u of t, e to the 2t? The derivative of this, I got to use the product rule. I get the derivative of the first times the e to the 2t. Derivative of the first times the second plus the first times the derivative of the second, e to the 2t times 2. All right, so let's remember that u is a function of t. And as we do in differential equations, one of the things that makes it kind of hard is sometimes we drop the of t. So just u, but remember that u is a function of t. So if I do this, I get u prime, okay, e to the 2t. We like to put the 2 in front, plus 2u e to the 2t. So suppose I take d minus 2. Look at that, d minus 2. Well, suppose I take d minus 2 acting on u e to the 2t. I get, well, let's write it out. I get the first thing is d acting on u e to the 2t minus 2 times u e to the 2t. All right, that's just multiplication, but this is derivative. I've already done that. That's u prime e to the 2t plus 2u e to the 2t minus 2u e to the 2t. Voila! Voila! That part cancels, and I just get u prime e to the 2t. Cool. So let's rewrite that formula right up here. So if I take d minus 2 acting on u, function of t, e to the 2t, I get u prime e to the 2t. Now, what happens if I act d minus 2 acting on u prime e to the 2t? This formula works for any function, including u prime. So I just get u prime prime e to the 2t, right? This formula implies that. But this one here is really d minus 2 squared on u e to the 2t. So d minus 2 squared, and d minus 2 on d minus 2 is u double prime e to the 2t. And then it also follows that d minus 2 cubed acting on u e to the 2t is u triple prime e to the 2t. All right. So if instead of just plugging in u is e to the RT here, I find that r's got to be 1. So instead I plug in e to the 2t, but of course I get, that's a solution, but then I plug in u is y is any function u of t times e to the 2t. And I find that I get u triple prime e to the 2t. So that should be 0. Set equal to 0 to get a solution to the ODE. The ODE is d minus 2 cubed y is 0. So if this y is a solution, then u triple prime is 0. Right? Because e to the 2t ain't never 0. All right. Oh, but this, we know the solution to this. All right. So what function has a triple derivative that's identically 0? Well, that's any quadratic function, right? Because derivative of t squared is 2t. Second derivative of t squared is 2. Third derivative of t squared is 0. Fourth derivative is 0, etc. All right. So that means that u of t is c1 plus c2t plus c3t squared. Right? 3 arbitrary constants, so the general solution. So therefore, the general solution to d minus 2 cubed y equals 0 is that u times e to the 2t is y is c1 plus c2t plus c3t squared all times e to the 2t. All right. So hopefully seeing that will help you memorize the rule. I don't know. You can just memorize the rule. This is just sort of a bonus. Okay. Cool. And of course, this 2 could have been any number. That 3 could have been any positive integer, right? That could be a 5. It could be a 1. It works if it's 1. It could be a 7. And if that's d minus 2 to the 7th, I just keep going c1 plus c2t plus c3t squared plus dot 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 plus c7 times t to the 6th e to the 2t, right? All right. Well, thank you for listening.